This video is going to talk a little bit about the unit circle and how we can kind of work from, instead of talking about angles all the time, what about if we start talking about the trig functions, right? Let's get ourselves into some good trigonometry. Now, the unit circle can be a very helpful shortcut when it comes to finding some trig values. So you'll notice we have two questions over here at the right. Find the coordinate of the point when t equals 7 pi over 6, where t is the distance along the edge of the circle starting at 1, 0. Now notice if that's a circle of radius 1, right? We've got these points around the edge, they're all exactly 1 unit out. Well, 7 pi over 6 is that same idea. 7 pi over 6, the distance along the edge of a circle, essentially saying the radians along the edge of a circle. Well, if pi over 6, remember, was 30 degrees, then we want to go 7 pi over 6. We want to go 7 times 30, or essentially 200, right? And 10 degrees, leaving ourselves a 30-degree angle between this line and the x-axis. Well, in that case, we could draw ourselves a nice triangle, right, with that 30-degree angle there. And remember that a 30, 60, 90 triangle has side lengths of 1, 2, and the square root of 3, right? We know that. Only remember, this is a circle of radius 1, so I can't call that 2. I need to divide by 2. I need that radius to be a 1. If I divide one side by 2, I'm going to divide all sides by 2. And now, to name that coordinate, right, to identify that coordinate, all I need to realize is, in the x direction, we went left root 3 over 2 units, and we went down, so negatively 1/2 unit. And there's our coordinate point for the angle 7 pi over 6. Now, down at the bottom, we're not talking about just finding a coordinate. We want to find the trig functions. So find all 6 trig functions of the angle formed by a line from the origin to the given point. So now we've got the given point up there, 5/13, 12/13. Well, now 5 is a little shorter than 12, so I'm not going to put that where that black dot is. I'm going to go ahead and draw this a little higher up here. But essentially, we've got a triangle going on where this was 5/13 and this was 12/13, right? As far as where that point would fall. Well, now the same idea as last time. Technically, if we're dividing both sides by 13, why don't we multiply them both by 13? So that our radius, instead of being 1, would actually be 13. And we could get rid of those denominators, right? So that now when we think about the sine of the angle, right, from the origin, from that central angle, we can just say, very simply, see if I can get my trig functions up here. The sine of an angle, remember, is equal to the opposite over the hypotenuse, or the sine would essentially be 12/13. The cosine is always the adjacent over the hypotenuse, right? 5 was adjacent to that central angle, and the tangent would be the opposite over the adjacent. Well, now you'll notice 12/13 was our y-coordinate. 5/13 was our x-coordinate, and really, tangent was just that y divided by that x, right? Those 13s would have canceled, and we just basically get our rise divided by our run, right? Tangent, 12/5 there. Couple of shortcuts for us. The the sine of an angle is really equal to the y-coordinate on a unit circle. The cosine is the x-coordinate on a unit circle, and the tangent is y divided by x on the unit circle. And in that case, if we want the other 3 trig functions, remember that the cosecant is the reciprocal of the sine. So we can very simply say 13/12. The secant is reciprocal of the cosine. Remember, the cos never go together, so we're definitely not doing, right? Not going to do, right? Big old X there. Not going to do cosine with cosecant. Cosine goes to secant, which again would be 13/5. And again, tangent goes to cotangent, which means 5/12. Let's take a look at that unit circle and how we can take advantage of it in a few different ways. A few different rules that we have. So again, note those rules that we had on the first screen. Sine is y, cosine x, tangent y over x, and the reciprocals sort of follow suit. The odd and even functions are a couple other things we can use. We'll show you those in a minute. The sine and the tangent would be considered odd functions. If you remember that odd functions, a negative inside is as good as a negative outside. It's sort of like reflecting twice, right? You reflect from quadrant 1 over to 2 and then down into 3. You do a 180-degree rotation, right, to make an odd function. Whereas the cosine is an even function. Cosine of negative theta is as good as saying cosine of theta. You can reflect any cosine measurement from the right side over the y-axis and you'll get the same measurement on the left side. Again, those are odd and even functions. We'll take advantage of that a little bit here in a minute. And then we'll also talk about periodicity. We'll bring that back up here in just a second. One thing we do want to note is positive values. Those can sometimes be helpful. All trig functions are positive in quadrant 1 because, again, x, y, and their ratios will always be positive in quadrant 1. The sine, on the other hand, because it's the y-coordinate, right? Sine being the y-coordinate would still be positive in quadrant 2, but would have been negative down below here, right? So only the sine, because only the y-coordinate, right, not the x, being positive in quadrant 2. Cosine would have been positive in quadrant 4 out to the right. And tangent, because it's the ratio of the two, is positive where we're dividing either positive by positive or negative by negative. So again, tangent will be positive down in quadrant 3. Let's see how we can take advantage of all of that. The sine of pi over 4. Pi over 4, note to self, again, is a 45-degree angle, which we know is a 1 square root of 2. But again, if we divide all sides by root 2, hypotenuse becomes 1, and the other sides become root 2 over 2. Square root of 2 divided by 2. Follow the numbers, do the rationalization, you'll find that out. Again, sometimes it might be easier to actually write it out. So again, let's do it the long way. Why not? Let's take our opposite, which would have been root 2. Sorry, let's get rid of all of this here. Let's do this the good old-fashioned route. What if we did go with just a nice long triangle, 1, 1, and root 2? Well, again, the opposite divided by the hypotenuse would be 1 over root 2. And if we rationalize, we get root 2 over 2, or basically, like we said, the y-coordinate of the point on the unit circle at 45 degrees, right, at pi over 4. The cotangent at negative 5 pi over 4. Now remember, tangent I said was an odd function. So the cotangent is also an odd function, right? The reciprocal wouldn't change that sign around. So you can actually find the negative cotangent of 5 pi over 4 if you'd prefer. And remember that 5 pi over 4 is down here. All right, that's 5/4. Cotangent being, again, if tangent is y over x, cotangent would be equal to x over y. So let's go ahead and take negative root 2 over 2 divided by negative root 2 over 2. But now again, that would have been at 5 pi over 4. We need to attach that negative from in front, right? So we're going to end up with a negative. Notice we're dividing something by itself, so a negative 1. Or if we had just traveled negative 5 pi over 4, notice we would have divided, again, x over y, negative root 2 over 2 divided by root 2 over 2 would have also come out to negative 1. You could have traveled that either way. Go to the actual angle or take advantage of that odd function idea. Talk to the teacher if you have any more questions about that. That's a little bit confusing, I get it. Last one for you is what's called periodicity. So periodicity is just the idea that we can go around the circle numerous times. If I'm talking about a 30-degree angle, right, I've got a nice coordinate to help me with my sine and my cosine. But I could also travel 390 degrees, right, a full circle plus 30 degrees, and I'm going to get the same ratios. I'm going to get the same coordinate here. So again, you can travel 2 pi, a full circle, around our circle, as many times as you want. That's what this n represents. We can go as many cycles as you want, around and around and around, but it's that final angle that really matters. So the sine of 2 pi plus theta is really the same thing as the sine of theta. The sine of 4 pi plus theta is the same thing as the sine of theta. You can go around and around and around that circle. So find the coordinate on the unit circle at 23 pi over 3. Well, the first thing I'm going to do is say that 23 pi over 3 minus 6 pi over 3 is really 17 pi over 3. If we subtract another 6, that would be 11 pi over 3. You subtract another 6, that's 5 pi over 3. And now that is a much more useful number, because 5/3 of pi, well again, 1/3, 2/3, 3/3, 4/3, and 5/3, right? We've got our coordinate point down here. Using or taking advantage of our triangle, 5 pi over 3 is 1/2 negative root 3 over 2. 1/2 negative root 3 over 2. And again, we can double check our answer very quickly and just make sure we got things right. Now, we could have drawn our own picture as well, by the way, so don't feel like you need to memorize that picture over there at the right. If we know that it's 5 pi over 3, we could just go over here and say, okay, well, I know that's 60 degrees down here into quadrant 4, right? My right angle being over here, but I know that that's going to be a 60-degree angle, which makes this 1, 2, square root of 3, and again, I'm negative square root of 3 because we went downwards. So when we're talking about the cosine and the sine, the cosine being the adjacent over the hypotenuse, 1/2, and the sine being the opposite over the hypotenuse, or negative root 3 over 2. We can draw our own pictures whenever needed. Talk to your teacher if you have any questions about that. Otherwise, good luck and have a great day.